I'm going to show you some examples using the pH scale, the decibel scale, and the Richter scale. So first example is using the pH scale. Find the pH if the hydrogen ion concentration, I believe that's called hydronium, the hydrogen ion concentration is 0 decimal, got 5 zeros there, 2, 4. I'm going to find the pH. Now the pH scale is defined as the negative log of the hydrogen ion concentration. So I just want the negative log of decimal and then 5 zeros to 4. I'm going to find the log of that. It gives me negative 5.6, and then I'm going to make that a negative, which gives me 5.6. So if you have an acidic solution where the hydrogen ion concentration is decimal 0.0000024, it has a pH value of 5.6. Again, the point of the pH scale, you can look at the introduction to this. The point of it is you've got this wide variety of hydrogen ion concentrations possible for acids and bases, and this gives you a manageable scale where you can easily compare and look at the numbers. Okay, now let's try this backwards. Find the hydrogen ion concentration. So let's find the H+, the hydrogen ion concentration, if the pH is 6.7. So that's somewhere near neutral. Remember, the pH is the negative log of the hydrogen ion concentration. So 6.7 is the negative log of the hydrogen ion concentration we're looking for. Okay, how do you solve this? Well, let's make that a negative 6.7 is the log of our hydrogen ion concentration. This is the log form. We convert it to the exponential form. So our hydrogen ion concentration is 10 to the negative 6.7. If you're unsure how to do this, look at the introduction to logarithms. You need to be able to work seamlessly between the log form and the exponential form. So this is 10 to the negative 6.7. You can use your calculator for that. 10 to the exponent 6.7, and that gives you 1.995 times 10. Sorry, that gives you 4. Let me clear the history on here. So 10 to the negative 6.7 is Yeah, 1.995 times 10 to the negative 7. Sorry, just getting used to reading the scientific notation off of the calculator on my computer. So you could also write that as 0.12345 1995. That's the H plus ion concentration if your pH value is 6.7. Okay, let's look at an example of sound intensity. So if you have a lawnmower is 100 decibels. This is a particular lawnmower. They could be different one to the other. A lawnmower is 100 decibels, and a conversation is 60 decibels. How many more times intense is the sound of a lawnmower compared to a conversation? How many times more intense is the lawnmower? Okay, so we have an increase of 40 decibels. A 40 decibel increase means you're going times 10 to the 4. You see, you multiply by 10 for every 10 decibels. If you go up by 40 decibels, you multiply by 10 repeatedly, 4 multiplications by 10, or 10,000. So a lawnmower is 10,000, or 4 zeros, 1 and 4 zeros, 10,000 times as intense as a conversation. Okay, and how do they compare to, so what is the actual intensity of them? So this is how they compare to one another. What is the actual intensity, sound intensity of a lawnmower, and what's the sound intensity of a conversation? So let's look at sound intensity. So the decibel scale, a decibel is 10 times the log of the sound intensity of the sound that you're considering, divided by the threshold intensity of human hearing, where the threshold intensity is 10 to the minus 12. So for a lawnmower, let's say I'm looking for the I value, the intensity of sound from a lawnmower. So lawnmower is 100 decibels. So let's take that 100 decibels, and that is 10 times the log of the intensity of the lawnmower divided by 10 to the minus 12. Divide both sides by 10, so 10 is the log of I over 10 to the minus 12. So let me just slow down for a second here. This is your definition of a decibel. There's a 10 in here because that decibel means it takes 10 decibels for a single tenfold increase. So you go up by 10 and that's times 10. You go up by 20, that's times 100. And we're taking the log of the fraction of the intensity of sound under consideration divided by a reference. Now the reference is the quietest sound that can be detected by a human ear. And that is a sound where you have 10 to the negative 12 watts, that's our unit of power, per meter squared. So any other sound, we just look at the fraction of that over 10 to the minus 12, take the log of it and multiply it by 10, and that's how we get the sound in decibels. So we need to work backwards to find the sound intensity. So starting out with a lawnmower with 100 decibels, 100 is equal to 10 times the log of the intensity over 10 to the minus 12. Divided both sides by 10, and now I'm going to put that into exponential form. So this is a base 10 log, my exponent is a 10, and that gives me my intensity over 10 to the minus 12. Again, you must get seamless at going from log form to exponential form. Let's multiply that up, so I've got 10 to the 10 times 10 to the minus 12 is equal to I. So that's 10 to the minus 2, or decimal 0.1. Or 1/100th. So that is the intensity of sound that I'm looking for. Okay, what's the intensity of sound of a conversation? So remember, a conversation is 60 decibels. So the sound level of a conversation is 60 decibels, and I want its intensity. My decibel value is 10 times the log of the intensity under consideration over the reference intensity. And again, the reference intensity is 10 to the minus 12. So I have 60 decibels, and that's equal to 10 times the log of the intensity of sound of a conversation over 10 to the minus 12. So divide out the 10. And now convert that to exponential form. Multiply that up. And this gives me 10 to the minus 6. Or 1/1,000,000th of a watt per meter squared. Again, the whole point of this log scale is we've got this wide variety of numbers that become very difficult to compare. And by taking the log of those numbers, multiplying by 10, it gives us this reasonable scale, where 0 is the threshold of human hearing, and 100 is this loud sound that's going to hurt and bother you, like being right next to a lawnmower. The scale doesn't just go from 1 to 100. A jet engine has a decibel value of about 160, and decibel values can actually be negative. You see, if a human ear barely detects 0 decibel, imagine a dog. A dog can hear much quieter sounds than a person can, so their hearing range would go from the negative end of the decibel scale. Okay, let's do an earthquake example here. So we're going to compare a 5.2 earthquake to a 2.5 earthquake. Compare a 5.2 earthquake to a 2.5 on the Richter scale earthquake. So the Richter scale, magnitude of an earthquake on the Richter scale, is the log of the intensity of the earthquake divided by a reference intensity, and that reference intensity is a low-level earthquake. It used to be the lowest level detectable by a seismograph. So that would be the machine that's used to measure movement or vibration in the earth, and the lowest detectable used to be the reference value. Now we keep the same reference value so the scale doesn't change, but modern machinery can detect even smaller movements in there, which means you could potentially end up with negative values on the Richter scale. And that doesn't mean a negative earthquake. That doesn't make sense. It's just a really low level, and current machinery is capable of detecting that. So if I0 was the lowest level detectable, then if you have an earthquake of magnitude I0, then I0 over I0 is 1, the log of 1 is 0, that would be 0 on the Richter scale. Because it's the base 10 log, every time you go up by 1, that's a 10-fold increase. So if you go up by 2, that's 100. If you go up by 3, that's 1,000. So if you compare these two numbers here, 5.2 minus 2.5 is 2.7. So how do you compare these earthquakes? Take 10 to the exponent 2.7, and that's how many times greater in magnitude the 5.2 earthquake is compared to the 2.5. 10 to the exponent 2.7. So it's going to be greater than 100 and less than 1,000. 10 to the 2.7 is 501. Again, between 100 and 1,000. So you have 500 times the magnitude, 500 times the intensity of movement of the Earth when the earthquake has a value of 5.2 compared to 2.5. Let me just write out the formulas for each of these. So you've got the pH scale. The pH scale is the negative log of the hydrogen ion concentration. The decibel scale, we throw a 10 in there so that our scale goes 0 to 100 instead of 0 to 10, times the log of the intensity of the sound you're considering divided by the threshold intensity of human hearing. And in the Richter scale, that is the log of the intensity of your earthquake over a threshold intensity again. In all of these cases, you're taking the log, and the reason why you're taking the log is it takes these widely varying numbers and brings them down to a smaller scale that's easier for you to understand.